Breaker, breaker, breaker. We are live. Welcome back. For those of you who missed what I was talking about in my previous lecture, I just want to say this is proof that it functions. I ran this through PyCharm. So let me just give you a quick breakdown of what I've done here before we dive in. It'll be fun. I'm not going to spend too much time on this, but I just want to clear things up for those of you who may not understand. So once again, I'll show you the equation. This is the equation. Here's the equation. These are the isotopic tachyonic system equations. And these isotopic tachyon, this is the isotopic system numerical solver right here. I put this in PyCharm and it works. So if you didn't understand what I was talking about in my previous video, you guys, I have something else for you right here. So I put this into Claude. This is Sonnet. If you just read what's on the screen right here, it will tell you what each of these symbols mean in terms of the equation. You see we have a bunch of weird symbols here in terms of the equation. And you don't know what it means, right? So if you read what's on the screen here, I can read it for you guys, but I'm just going to let you guys read this and then I'll scroll back. Okay, enjoy. You can take a picture of your screen, do whatever. Okay, I'll be right back. Talk to you in a bit. All right. All right, so I used Claude to analyze the equation I showed you in my previous lecture. Right, these are the isotopic tachyonic system equations, and this is what they actually mean. So, here you go. There we go. The first equation describes quantum state as a superposition of isotopic states. Oh, give me a second. Testing, testing, 1, 2, 3. The first equation describes a quantum state as a superposition of isotopic states similar to standard quantum mechanics, but with an additional isotopic index, I. This suggests that we're tracking different isotopic configurations simultaneously. It's right there. Just read it. Let's go on to number 2. The tachyonic term introduces faster than light considerations through a modified stress energy tensor. The negative mass term is a characteristic of tachyonic systems. So just keep that in mind. Let's move on to number 3. I'm sorry I'm rushing you guys. I had an energy drink and I'm very hyper right now. Number 3, let's go on to number 3. The combined Hamiltonian merges standard quantum mechanics, kinetic potential terms with a tachyonic modification through an imaginary coupling constant. Did you hear that? The coupling constant is actually theoretical, which means it's imaginary. That's pretty crazy, right? Anyway, this AI implemented a numerical solver for these equations if you're having trouble using them. And this is the Isotopic-Tachyonic System numerical solver. I'm just going to scroll over the code right here so you can see it. Here's the code, blah, 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 blah. There's the code. You saw the code. I'll show you more of the code. Let's just scroll through here. I've implemented a numerical solver for the system that handles the isotopic state evolution using a spatial grid and multiple isotopic components. Implements a tachyonic modification through a simplified version of the whatever term, because I don't know what that means. I don't even know how to pronounce that. Do I look like I speak Greek? I don't speak fluent Greek. Anyway, use a split operator method of for time evolution visualize includes visualization capabilities for the probability density. And here are the key features of the implementation. I'm just going to highlight this. Some key features of the implementation. The solver uses finite difference methods for spatial derivatives. The isotopic potential can be customized for each isotope state. The tachyonic term is implemented as a local operator. The evolution preserves normalization through this should be monitored in practice. Would you like me to explain any aspect of this implementation in more detail to modify the solver to focus on specific features of the system? Let's just go into Claude and type in yes, please, and be polite. Yes, please. Yes, please. It's asking a question. We press enter, and it said I answered it, and now it's refining this equation. We're just gonna simplify it into something nice. But for now, this is what we're dealing with. Here's the actual code in PyCharm. Here's the actual code in PyCharm. So look at this. This is the actual code in PyCharm. Look at that. There's a really good song playing on the radio now. That's why I'm bopping my head. I'm allowed to bop my head. People don't make fun of me. If you do want to make fun of me, please make it a good joke and make it accurate. Okay. Anyway, here we go. This is the code. I don't know what to tell you guys. Just put this in your computer and try it. This is code. It's code. Um, let's just go to the top. Um, let's just close. Let's have this. You can't really see the code. Okay, so here we go. Let me just, oh, this is the import statement. We don't need to see the import statement right now. Let's just, okay, so there we go. I'm going to do this. 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 Oh, shit, shit. Sorry for swearing. Um, uh, there you go. And I did all of this with artificial intelligence. I used Claude AI. I used Claude AI. I used Claude Sonnet to do all of this, like literally this morning. And then now I'm looking at the code. Anyway, let's have a conversation about quantum computers while I drink my coffee. You want to talk about quantum computers? What is a quantum computer? How does a quantum computer work? How does the chip work? Why is it so big? Does it need to be that big? No, it's just a chip this small. The size of that machine is actually the cooling mechanism, but we'll dive into that after these short messages.
These short messages.
A quantum computer is an advanced computer that uses the principles of quantum mechanics to perform calculations at speeds unattainable by even the top supercomputers of the modern world. To understand how a quantum computer works, imagine that you're playing a game of chess and want to predict all the possible moves your opponent might make. You can do this with a classical or regular computer. It will go through each move of your opponent one at a time until it runs through all possible moves. This process, as you can imagine, can be time-consuming. However, if you had a quantum computer, it would simulate all possible moves of your opponent at once, in a fraction of the time the classical computer took. This is similar to what a quantum computer can do in the realm of analysis and computation. A quantum computer and a classical computer are similar in some ways. Both have circuits, chips, and logic gates to process information, and they are both operated by algorithms. However, the primary difference lies in how they process information. Classical computers use binary bits, zeros and ones, representing the on or off state of a current. Quantum computers, on the other hand, use qubits, which can exist in both states simultaneously, a property known as superposition. This unique ability of qubits opens up a world of possibilities, allowing quantum computers to process information in a fundamentally different way than binary bits, and potentially revolutionize the future of technology. Let's consider the concept of superposition using an everyday example. When you flip a coin, it can show either heads or tails. But when the coin is spinning in the air, what state would you say the coin is in? Is it heads or is it tails? While it's spinning in the air, it could be argued that it's both heads and tails, correct? Similarly, qubits can exist in both the 0 and 1 states simultaneously. In a quantum computer, a system of multiple qubits can simultaneously possess multiple states, allowing the quantum computer to process many solutions simultaneously, something a classical computer simply cannot do. This capability enables quantum computers to solve problems much faster than classical computers. The magic of quantum computers doesn't end with qubits and their multiple states. Can be linked to each other, or in the language of quantum mechanics, they are entangled with each other. Entangled qubits work in a way that the operations of one qubit can influence other qubits, no matter how far apart they are, and can also influence the entire system. This allows for significantly higher computational power, something that classical computers cannot achieve. Entangled qubits function seamlessly due to a phenomenon called quantum entanglement. We have already made a dedicated video on quantum entanglement, and the link is in the description. Additionally, a quantum computer looks nothing like your regular computer or laptop. When you walk into a room housing a quantum computer, what you'll most likely notice first is large, complex-looking machinery, much like a chandelier, with golden, silver, and blue parts. Around it is a maze of wires, tubes, and other intricate components. The setup looks straight out of a sci-fi movie. Quantum computers have been in existence in various forms for several years. In fact, some tech companies already possess operational quantum computers that serve as valuable resources for software development and programming languages. The most significant advancement in quantum computing in recent years occurred in October of 2019, when Google asserted that it had achieved quantum supremacy with its quantum computer. This entailed using their specialized Sycamore processor to perform a specific type of computation much faster and more efficiently than the most powerful classical supercomputer. This demonstration of quantum supremacy validated the concept that quantum computers can indeed surpass classical computers in specific tasks by leaps and bounds, and can execute operations that classical computers cannot. This progress also prompted other companies, such as Microsoft, IBM, and several startups, to intensify their quantum research in pursuit of even greater results. Once the full potential of quantum computers is realized, it will herald a world of truly unimaginable possibilities. Quantum computers have immense computational capabilities that will greatly enhance artificial intelligence. Quantum cloud computing services have the potential to revolutionize machine learning by processing extensive amounts of data and complex calculations at unprecedented speeds. In cybersecurity, quantum computers could uphold data encryption during active use, providing robust protection. They are also poised to revolutionize medical and drug research, weather forecasting, and automobile battery technology. While it will take many years before quantum computers become mainstream and see large-scale commercial use, it doesn't seem like an exaggeration to say that quantum computers will eventually be powerful enough to not only solve complex problems, but also help you find your missing socks, predict the outcome of your next dinner date, and maybe even explain why you walked into the kitchen only to forget why you were there in the first place. When a pair of electrons are generated,
let me show you how we do stuff around here. Actually, my department uses monday.com, so I'm good. The work map.
Imagine that you're on a long drive when you suddenly hear your stomach begin to grumble. You decide to head to a fast food drive-thru and you order a hot dog and a hamburger. They are put in similar boxes and handed to you through the window. You have no way of knowing which box has the hot dog and which has the burger. Obviously, once you open one of the boxes and see a burger, you will immediately know that the other one has the hot dog. This means that the hot dog and the burger are entangled in a certain way. This is roughly the idea upon which quantum entanglement is based. Look around you. Everything you see, perceive, and interact with in the real world follows the rules of classical mechanics. This is a study of the motion of bodies in accordance with the general principles first laid down by Sir Isaac Newton. But what about objects that are really, really small? Do they also follow these same laws of classical mechanics? Believe it or not, the answer is no. When things get that small, quantum mechanics takes over, and things start to get extremely weird. Quantum mechanics is the language of tiny particles like photons, the particles that make up light, and the particles inside an atom, such as protons, neutrons, and electrons. To give you a rough idea as to the size of these particles, consider this. The tip of a needle is so large that it could fit billions of electrons. That is how incredibly small electrons truly are. Now that you have a general idea of the size of electrons, let's talk about identities. If someone were to ask, "Who are you?" what would you say? Probably your name, right? Now, let's assume that an anthropomorphic raccoon from another planet asks you the same question. What would you say then? Perhaps, "I am Peter Quill, a human from Earth." In this case, you specified 3 levels of identification. Similarly, in a 3D space, X, Y, and Z coordinates are used to specify an object's exact location, as no 2 objects can have the same X, Y, and Z coordinates. If you consider a 4-dimensional space, with time, t, as an additional dimension, then no 2 particles can have the same 4 coordinates. In the same way, an electron has 4 levels of identification, consisting of 4 quantum numbers. Every electron within an atom has a unique set of quantum numbers. No 2 electrons can share the same combination of 4 quantum numbers. Electrons can be identified using these 4 quantum numbers, which are called the principal quantum number, the orbital angular momentum quantum number, the magnetic quantum number, and the electron spin quantum number. All of these quantum numbers are very important, as they help determine the electron configuration of an atom and the probable location of electrons within that atom. However, for the scope of this video, we're only going to talk about the electron spin quantum number. The definition of spin is the intrinsic value of the angular momentum of a fundamental particle. An electron can either have a positive spin, called spin up, or a downward spin, called spin down. Now, this is where things get bizarre. When we say an electron has a positive spin or a negative spin, it doesn't mean that the electron is actually spinning. Although it does have angular momentum and proper magnetic orientation, it's not exactly spinning. It may actually exist in the state of superposition when it has both a negative and positive spin. You may find the idea of superposition confusing because this doesn't seem to go along with our perception of the real world. To help explain this a bit better, here's a famous example for understanding superposition. You might have heard of Schrödinger's cat. This is a famous thought experiment devised by Austrian-Irish physicist Erwin Schrödinger. It goes something like this. Imagine that you put a cat inside an opaque, soundproof box, along with a radioactive substance, a vial of poison, and a Geiger counter. If the radioactive substance decays, then the Geiger counter triggers a setup that releases the poison, thus killing the cat. However, the decay of the substance is a random process, so there's no way to predict when it will happen. And that is why, before opening the box, you can say that the cat is in a superposition of being both alive and dead at the same time. In the same way, when a coin spins on a flat surface, it's in a state of superposition between its two faces, heads and tails. Similarly, electrons in their natural state exist as a superposition of both up and down spin. Only when measured do they give a definite value of up or down, which, in technical terms, is referred to as the collapse of the wave function. In quantum mechanics, wave function collapse occurs when a wave function, which was initially in a superposition of a few states, reduces to a single state due to interaction with the external world. When a pair of electrons are generated, interact, or share spatial proximity, their spin states can get entangled, which is what scientists call the quantum entanglement of electrons. Once the electrons are entangled, the two electrons can only have opposite spins. That is, if one is measured to have upspin, the second immediately becomes downspin. Now, we know that the two electrons, unmeasured, do not have a single spin, but a superposition of both up and down spin. If we were to separate the two electrons arbitrarily far, say, we put one in a physics lab on Earth and another in a different lab somewhere in the Andromeda galaxy, and we measure the spin of the electron on Earth, we will immediately know the measurement of the one in the Andromeda galaxy. For example, if we measure the Earth electron to have upspin, we immediately know that the other electron has downspin. This information traveled instantaneously, faster than the speed of light. As one can imagine, this idea greatly bothered famous physicist Albert Einstein. It was such a disturbing realization, in fact, that he called this phenomenon spooky action at a distance. So how can this spooky action at a distance be useful to us? Well, let's start with one of the most common everyday objects, the clock. Having a common synchronized clock is very important in today's world. They keep things in line, like stock markets and GPS systems. Today, we have extremely precise clocks, known as atomic clocks. The quantum logic clock at the U.S. National Institute of Standards and Technology, NIST, in Colorado, will neither lose nor gain 1 second in some 33 billion years. Entangled atomic systems would not be preoccupied with local differences and would instead solely measure the passage of time, effectively bringing them together as a single pendulum. That means adding 100 times more atoms into an entangled clock would make it 100 times more precise. Entangled clocks could even be linked to form a worldwide network that would measure time independent of location, vastly expanding the technology of GPS systems and telecommunication. Then, of course, there's quantum cryptography. As a kid, did you ever make up a secret code language that only you and your best friend could understand? Imagine that, but with the key to cracking the code being randomly polarized photons entangled with each other. That is quantum cryptography. Today, some tech companies use QKD, quantum key distribution, to design ultra-secure networks. In 2007, Switzerland tried out an ID Quantique product to provide a tamper-proof voting system during an election. This system promises to be highly secure because if the photons are entangled, any changes to their quantum states made by intruders would be immediately apparent to anyone monitoring the system. Researchers at Japan's Hokkaido University developed the world's first entanglement-enhanced microscope, using a technique known as differential interference contrast microscopy. Using entangled photons greatly increases the amount of information the microscope can gather, as measuring one entangled photon gives information about its partner. How about quantum teleportation? Is it possible? Yes, teleportation is possible in the world of subatomic particles, but it's entirely different from the way teleportation is depicted in movies and popular culture. Quantum teleportation involves the transportation of information rather than the transportation of matter, which is the specific type of teleportation typically focused on in science fiction. Physicists continue to delve into and understand more about the capabilities of quantum entanglement. Once we are able to fully harness this knowledge, it could potentially revolutionize every aspect of our existence. Until then, we will continue to try and make sense of the principles of quantum mechanics because, let's face it, it's a strange branch of science that doesn't seem to make any sense in the real world. Basically, as